Now, okay, we can look at another problem. A block 1 of mass 1 kilogram slides from rest along a fractionless ramp from a height of 2.5 meters, and then collides with stationary block 2, which has mass 2 kilograms. Okay. After collision, block 2 slides into a region where mu k equals to 0.5 and comes to a stop in distance d within that region. Okay. So for this problem, I guess you have to draw the picture, otherwise you don't even know what they are talking about. Okay. So we have to translate each sentence into some graph. Okay. Block 1 slides from a ramp. Okay. And the height .5 meter. It starts from rest, okay, and collide with a stationary block 2. So you have block here released 1, M1 equals to 1 kilogram. You have block 2 here, M2 equals to 2 kilograms. So there will be some collision happen here. After that, the block 2, okay, after collision, the block 2 will acquire some velocity and move forward. Okay. And after that, we have some region where you have frictional force. Okay, mu k equals to 0.5. So you have some rough surface here. Mu k equals to 0.5. Due to the frictional force, the block 2 will finally stop, okay? And the stop distance in this problem is the quantity we want to find. Okay. Okay, that's kind of what happened here. So you need to have a picture like that in your mind. That's what happens. A block slides down, collide with the second block, and so the second block will be pushed off and finally stops due to the frictional force. Okay? So that's one of the most important parts. You should be able to translate those sentences into a picture. Okay? So you can see to start the process, in fact, we have several different parts. Right? First, for block 1, it slides down along in frictionless incline. So itself a quite simple motion, right? We all know how to deal with it. And then you have a collision process. Okay? Do we know what kind of collision? Oh, completely inelastic. So even after collision, okay, they stick together. Okay, so there are some collision here. Question?
It's the last step.
Oh.
That's the paired homework, yeah.
Okay. So for elastic, maybe the block 1 will bounce back, or maybe moving to that direction with a slower velocity. We don't know. Okay, but we know for elastic collision we have both momentum conservation and what do we have? Yes? Kinetic energy conservation. Okay, so that's some solution. So the second part is the collision process. And then for block 2, it has a slowing down process, right? Okay, finally stop here. So you actually, when you try to consider this problem, you have to realize there are 3 different parts. Each part, you know how to deal with it. So you just need to connect them together. Okay. Any question here?
Why are you only measuring the frictional distance?
What's the question?
Why are you only measuring the frictional distance and not from the initial drop?
Not from here, you say? It only matters for the part where you have frictional surface. And here, it may not have frictional surface. And this part wouldn't slow the object down, right? So that means, like say, after collision, the block 2 acquire like say 10 meters per second. Without friction, it will keep this 10 meters per second, unless it enters the regime. So only this part is the stopping distance or slowing down distance. It has nothing to do with how long this part, right? So the distance of this part, can you see, actually arbitrary. It wouldn't affect the problem. I can plot it to here or plot it to here. It wouldn't change the problem. Okay, because this part is frictionless. Okay? Any question here? Now, so we have 3 parts. So let's label this is A. We call this is state A. Just before the collision, we call state B. Just after the collision, we call C. And when it stopped, we call D. Okay. So we have process A to B, B to C, C to D. So for A to B, which equation can be used here? For A to B, the sliding process.
Conservation of momentum.
Mechanical energy, right? Okay. Yeah. Something sliding down along a frictionless incline. That's place where you can use mechanical energy conservation.
is conservation.
If it's frictional surface, you probably need to think about the total energy conservation. Okay? So A to B, mechanical energy conservation. So basically it says that Ka plus Ua equals to Kb plus Ub, right? And from B to C,
in order to have the conservation momentum,
what equation can be used here?
One explosion. The
In the
conservation of
collision
momentum.
process, you can always use momentum conservation. So it says that Pb, total momentum, okay, equals to Pc. It's an elastic collision. So you also have Kb equals to Kc. Okay. So first let's list all the equations you are going to use. And then for C to D, okay, by the way, we also need to see this is for block 1, right? From A to B, we started block 1. And for B to C, it's a collision process. So you need to consider both block 1 and 2. And for C to D, you are considering the block 2 only, right? That's also something you have to, you better put it here. So for C to D, what kind of equation can be used? So the block 2 is slowing down and finally stopped by the frictional force along the surface. What kind of equation should be used here?
Is it a Newton's second law?
of course, you can always use Newton's second law, but it should be quite complicated. Here, we need to think about all those equations we learned here.
Delta
those
K equals 0.
energy equation, momentum equation. Okay, Newton's second law is something we learned. Which one?
Delta K equals 0. I don't know the names of the formulas.
Okay,
I just
the energy changes, right? Mechanical energy changes, so it's finally stopped. And you have frictional force, so that kind of suggests you
the work done by a non-conservative force.
total energy conservation. Yeah. We call it total energy conservation. So delta E equals to W and C,
Yeah.
right, for C2D. Okay, you can see this is quite a comprehensive problem. You kind of use all the equation you learned for this part. Okay, but each of them is straightforward enough. Okay, so if you understand each process clearly, you should have no problem. You just need to connect them together. Okay, so let's do it one by one. Write down the exact equation, and I'm not going to solve it anyway. Okay. So the first, first equation, Ka plus Ua equals to Kb plus Ub for block 1. So, A to B is there any zero term here you can identify for block 1? Initial kinetic energy Ka. Anything else?
UB.
The final potential energy UB. Okay, you can choose it as 0. Of course, in this problem, you want to choose the ground as 0, right? So UB equals to 0. And then you have UA equals to KB. In other words, you have mg YA equals to 1/2 mVB. Okay. Let's call it VB1. Okay, because later we are going to use the velocity for VB2.
Is the A, is that the same as like the initial and final? The A and the B?
Yeah.
Okay.
Okay, because here I don't want to use the initial final because we have many initial and final states. So
Okay.
it's better label each of them as A, B, C, D. Okay. So from that, of course, you can solve for VB1, right? There's no problem. You have, all these numbers. Mass, do we know mass? Yes. Gravitational constant and the initial height 2.5. Okay? So now you know this quantity. And then you can go to the part B. Part B to C. From B to C, now you have a collision process. So it's something like this. Okay, 1, 2, 1, 2, and this is VB1, this is VB2 velocity, this is VC1, VC2. Okay, the initial velocity to final velocity, and so here VB1. You calculate it here, so you know some number. That's okay. And what's VB2? It's 0, right? Okay. It's VB2 0, not the clock. And then, what you really need is VC2. Okay. And then you are going to analyze block 2. But of course, here, you want to calculate VC2 and you have another unknown quantity. So in this problem, you have two unknown quantities, right? So you need both equations together to solve for VC1 and VC2, the two final velocities. That's a standard procedure for elastic collision, right? Okay. So you need write down the equation. Momentum conservation PB equals to M1 VB1 plus 0, okay, equals to M1 VC1 plus M2 VC2. And you also have the kinetic energy conservation. In this case, with 1/2 M1 VB1 squared equals to 1/2 M1 VC1 squared plus 1/2 M2 VC2 squared. Okay. So the two equations together will give you both VC1 and VC2. That's the quantity we need for the next step. Okay? So, for this part, we need to go back to check how can we deal with elastification. Okay, you can solve it, but it involves some tricks, remember. Okay, any question here? So now, we get VC2, the velocity of block 2 after collision. So now, the block 2 will move with that initial velocity and comes to this frictional part and finally stopped by the frictional force. And here we're going to use the total energy conservation, delta E equals to WNC, right? So here, so C to D, we want to use delta E minus, equals to WNC. And delta E equals to WNC, of course, should be KD plus UD minus KC plus UC equals to WNC. In this case, the only work done by the non-conservative force is the work done by the frictional force, right? Okay, so this is WF. Any question here? That's a work done by all the non-conservative force. In fact, here you have two non-conservative force. One is the frictional force, another is the normal force. But normal force doesn't do work. So the only non-conservative work is work done by the frictional force. Okay? And left-hand side, the change in the mechanical energy. The final mechanical energy subtracts the initial mechanical energy. Final state D, initial state is C for block 2. Right? So, what do we know about these quantities? There are many zero terms. How about kinetic energy?
K final.
Final kinetic energy 0. Okay, stopping distance. Finally stopped. And initial kinetic energy is calculated from VC2. And how about potential energy in this problem?
Both 0.
Both of them will be 0, right? There's both of them in the same height. Okay. So finally, you get, you have negative side here. You have negative Kc is 1/2 M 2. Okay, here is M1. Of course, it will be cancelled, so it doesn't matter. So 1/2 M2 VC2 squared, that's negative Kc, equals to WF. WF is the work done by the frictional force. So remember, it's negative Fk multiplied by D, right? Remember how we get, why do we have a negative side here?
This friction is oxidative.
Because, precisely speaking, it should be Fk multiplied by D multiplied by cosine theta. But frictional force is always opposite to the direction of the motion. So it's cosine 180 degree, which is always negative 1. Okay, so frictional work is negative Fk multiplied by distance. Okay. And so it can be written as negative mu k normal force n multiplied by d. Frictional force equals to mu k n. And in this case, the normal force should be the same as weight of the block Q. So it's negative mu k m2g multiplied by d, right? So that's the expression for the work done by the frictional force. So negative mu k m2g multiplied by d. So you can see, you know all these quantities. Mu k is given, VCQ you calculate from here. So you can solve it for distance d. Is that the quantity we want to ask? Yes. Okay? So you can see here, we just do it step by step from initial stage to the next stage, A, B, C, D, do it one by one. For each part, you just apply the appropriate equation to solve it. Okay? Any question here?